Hi, this is Mr. Rubenstein, and today I'm going to show you how Archimedes calculated out a very nice approximation of pi back in about 250 BC using only two geometrical theorems. One was very famous Pythagorean theorem, and the other is the less known angle bisector theorem. And the general idea of his proof that pi is approximately 3.14 was to take a circle that I have here, and this circle has a radius of a half, and that means the circumference of this circle is exactly pi. Well, to approximate the circumference of the circle, he drew a hexagon, a regular hexagon, circumscribes it around this circle. And he was able to calculate it out using geometry, and I'll show you the details of this in a little bit, but he was able to calculate out the perimeter of this hexagon to be exactly 3.46, and he would say that pi is less than that. Then his very clever idea was to increase the number of sides to 12 and find the perimeter of that 12-sided figure, and then to 24. And then again, he doubled the size to 48, and he stopped when he got to a 96-sided figure, and he worked out the perimeter of this figure to be 3.14271, which, for his purposes, was close enough for what he was trying to achieve. He was trying to show that pi was slightly less than 22 over 7, and this number is slightly less than 22 over 7. Well, I'm going to give you the details behind these calculations, and you could do these calculations with any calculator that has square root, division, adding, subtracting, and multiplying. Archimedes' proof relies on something called the angle bisector theorem. And here's the way the angle bisector theorem works. It says that if you have a triangle, like I have here, a triangle ABC, and I were to draw an angle bisector, in this case AD bisects angle BAC. Now, BD is not the same length as DC. AD bisects the angle BAC, but it doesn't, D is not the midpoint of that side. And it's not that obvious where it cuts that side. It turns out that in this case, it doesn't cut it in half, but BD is 2.51 and 3.73. The way you could calculate that out is using the angle bisector theorem. The angle bisector theorem basically says that that AB over CA always equals BD over DC. Now, this is not an obvious theorem, but I'm going to do a little proof of it in a second. This is a theorem that's, when it's taught in geometry, is taught around the time of similar triangles. And even though these two triangles, ABD and ADC, are not similar triangles, by drawing in a couple of extra lines, in this case I'm extending BA, and I'm drawing a line from C that's parallel to AD. And now, because AD is parallel to CE, the small triangle on top, ABD, is similar to the triangle on the bottom, EBC. And from this, I'm able to get some proportions. Now, from this picture with the similar triangles, we could say that that BD over DC equals BA over AE. This is E down here. Okay, that's something you can say from similar triangles. BD over DC equals BA over AE. Well, now I'm going to be able to prove that AE is actually the same length as AC, which would get us our angle bisector theorem. The reason this is true is we have here two parallel lines. That makes this angle congruent to this angle. Also, because these two lines are parallel, by corresponding angles, this angle here has to be congruent to this angle here. But remember, AD was an angle bisector, so that means that these two angles are equal, so I could actually put the double arc here, and that makes this. So what that means is that this thing is an isosceles triangle. And we're left with what we were trying to prove, which is the angle bisector theorem says that BD over DC equals BA over AC. Now this is a pretty unusual theorem and it seems not very useful. And usually the way this theorem is taught and the way it's used in elementary geometry textbooks is something like this. They would tell you the length. They tell you the length of 3 out of 4 of the pieces. Maybe the question would be something like this: if this thing's 12, and this thing's 16, and this DC here is 8, and they want to know what x is, they'd have you use the angle bisector and say something like x over 8 equals 12 over 16, and we'd end up with x equals 6. And that's pretty much where they leave it, so it does not seem like a very useful question. For the purposes of understanding Archimedes calculations, a much more useful question would be something like this. If this thing were 10 and this guy here was 20 and the entire length of BC was something like 25, the question is, how do you figure out how big DC is on its own? And that's not hard to calculate. What you do is, if DC is x, then BD is 25 minus x. Now the angle bisector theorem says that I can say that BD over DC is equal to AB over AC, which is 20. And then by cross multiplying, I get 500 minus 20x equals 10x. Bring the 20x over, get 500 equals 30x, which leads us to an answer of x equals 500 over 30, which is 50 over 3. Well, it's this sort of question is the way Archimedes is going to use it, where you know all 3 sides of the triangle and you're trying to figure out the length of one of the pieces of the line that's cut by the angle bisector. Well, that's all we have time for in this first part of this tutorial. But in the next 10-minute tutorial, I'll take you through the actual calculations that will end with us calculating the perimeter of the 96gon, and it will be extremely close to pi, though a little bit bigger than that. So now that you have the fundamentals, you have what you need to follow along on the calculations in the part 2 of this tutorial.